Before we begin Chapter 30, well, let's take just a minute and review Chapter 29. Essentially, the main concepts we covered in Chapter 29 regarding magnetic forces. So the first item that we covered was the force on a moving charge entering a magnetic field given by B. Now, as in the following videos, please take a moment when I ask you to pause the video and either try to recall an equation or answer a question or work out a problem. So pause the video and write down the force on a moving charge entering a magnetic field B. And of course that force is given by QV cross B, the cross product of the velocity of the charge and the magnetic field B. Now I show here a diagram of the velocity V and the magnetic field B. And the normal notation where the cross indicates the magnetic field going into the paper. On the right, I show a coordinate system where K, the Z direction, is going in the up, J, the Y direction in the right, and the positive X direction I hat out of the paper. Now, what is the direction of the force? Once again, pause the video and try to work out the direction of the force either by using the right-hand rule or by using vector analysis. What is the magnitude? Well, once again, take a moment and pause the video and work out the magnitude of the force. Of course, the magnitude is given by the charge times the magnitude of the velocity times the magnitude of the magnetic field times sine theta. Now, what is theta? Describe what theta is. Once again, pause the video and tell me what theta means, or tell yourself what theta means. Of course, theta is the angle between the velocity and the magnetic field B. Here it is 90 degrees as we have drawn it. Now let's look at the force on a length of current carrying wire. And that force is given by IL vector cross B, the magnetic field. Now what is meant by the term L as a vector? What does the length as a vector mean? Go ahead, pause the video and write down your answer. Well, L as a vector simply means one, L is the magnitude of L is the length of the current carrying wire that's in the magnetic field. And the vector portion indicates the direction of current flow. What is it in unit vectors? Pause the video and write down the unit vector representation of L as a vector. And that's given by L vector equal to L times J hat. Notice that I is in the direction of the Y axis, or the J hat direction. Now draw the force given when B is equal to BI hat. And I show the B, the magnetic field, in green. The circles with a period in the center represents the magnetic field coming out of the paper or along the positive X axis. And of course I can draw the force, and I show it here in gold, will be in the negative K direction. And you can verify that using the right hand rule. So take a moment and use the right hand rule to verify that I've calculated the direction of force correctly. And of course the magnitude is given by I, the magnitude of L times the magnitude of B times the sine of the angle between L and B. Now let's look at the torque on a current loop. We've covered two things. One, we've talked about the force on a moving charge in a magnetic field and the force on a current or a current carrying wire in a magnetic field. The point is, both these involve moving charge. Now, if we have a current loop, we can expect to see a torque on that loop, because let's look at the diagram that I've shown here. We have the magnetic field going in the positive Y direction, the current in the left-hand loop in the positive K, the current in the right-hand loop in the negative K. Now next to the loop I show another view, and the little diagram at the bottom which says viewing is meant to be an eye viewing from the bottom the current loop, and I show that in the next diagram. And I show on the right hand side of that diagram a X representing the current going into the paper and a period representing the current coming out of the paper. Now take a moment and try to figure out what the force is on the current loop on the left and the force on the current loop on the right. We can denote the surface area of that loop by vector A, and you should be able to explain to yourself what that vector A means. And we can also diagram the forces, where I have the force on the left loop pointing in the negative K direction and the force on the right side of the loop pointing in the positive K direction. Now let's calculate the torque, and the torque is given by I A vector cross B. Now you can immediately figure out from the forces what the torque will be around the central point right here. Okay, around that point. Let's see if our cross product works correctly, because if I look, it's going in the counterclockwise direction as viewed along the K-axis. In unit vectors, what is A? Of course, A is given by A I hat, which equal AB I hat. Now remember, the sides of the loop are A and B, and that calculates the area. What is B? Of course, B is equal to B J hat. Now, what do I need to do just to get the direction? So once I get the direction, I get the torque. Well, I need to form the cross product I cross J. And that's given me the magnitude of the torque times I cross J, which gives me a torque in the positive K hat. Well, torque in the positive K hat direction represents a counterclockwise direction, which is exactly what we figured out for the right-hand figure in the bottom. Okay, now that we've finished our review of chapter 29, we want to go on and start the preliminaries for Chapter 30.